right, let's get going from the current slide. Now, let's maybe even turn on the projector today. I don't know. Y'all need to see anything? Okay. We'll let the lights come on slowly, but they'll come on. Meanwhile, let me make a couple of announcements. First, sort of a good news, bad news situation. Okay, the bad news is Monday is a holiday, Labor Day. The school is closed. There's no classes. The good news is it doesn't affect us any because we meet on Tuesday, Thursday, so we won't miss a class. So I know y'all are delighted to hear that. Okay. Now, that being said, let's just talk about where we are, where we're going, how we're going to get there for right now. We're going to start in chapter 16 today, Earth and Space, and this basically, Justin, right?
Yes, sir.
Okay. Circle your name. Wait a minute. The other Justin. Okay, Justin Lindsay. Okay.
Yes.
I have another Justin who hasn't shown up yet. I thought I had circled your name. Okay, so where we are today, we're going to start in chapter 16, and then I want y'all to be sure to stop me. And here it is. I found you. I know you're here. Ishmael. Okay. All right. Be sure to stop me by 3:15. Okay? I want to give you a full 2 hours to do the lab and a full 30 minutes to do the test. Hopefully neither will take that long, but I want you to have that time available to you. So don't let me go past 3:15 in chapter 16. Yes?
When our test for Monday will be put in.
Say this again.
When our test for Tuesday will be put in.
I was in the process of grading. What I had to do since we last met was get all the grades from those little grade sheets that I had into my grade book. And that took way too long because I have some really big classes. And I had to get all the attendance in and all that done. So I just finished grading all of your labs and I just started grading your tests. So I don't even have them graded yet. I'm hoping tomorrow I'll have some fairly quiet office hours and I'm going to try to get caught up on just about everything. I don't know if I'm going to make it. If they come up with that we have to have contracts in tomorrow or something like that, then I'm going to be swamped again tomorrow. Last Friday, I got almost nothing done. I got there early, so I got about an hour or two done before people started coming in, and from that point on, I got nothing of my work done at all. So this week has been just about that way ever since. Okay, so we're going to be Earth and Space, chapter 16, for the first 2 hours, now less than 2 hours. Stop me by 3:15. Then we'll do the lab for chapter 15, and I have those run off and ready to go. And then when we finish the lab, and hopefully that won't take 2 hours, but when we finish the lab, we'll have the test on chapter 15. And I'm guessing that, just judging by the last test, y'all finished pretty quickly. So if that continues to be the case, then hopefully you'll be maybe able to leave a little early today. We'll see. Now, and then part of the answer to your question, while y'all are doing your test on 15, I will be trying to catch up grading on 14. But we'll see. Okay. I don't know if I'll get them in the system yet, but I'll get them as soon as I can. All right. Any questions? Good questions so far. Any other questions? Yes?
I got a question. Like the paper that I turn in, if we turn it in this month, we'll get 2 points.
4 points. Oh, no, you're right. 2 points, 2 points. This is a mini-term course. Okay, yeah. 2 points. Yeah, I'm sorry. 2 points this month, 1 point in September, and no points in, you just get your score in October. Yeah.
Do you prefer it for us to send it through our Lawson email, or can we just send it through our regular email?
Okay. It doesn't matter as long as you send it to my Lawson email. That's all that matters. But now understand this. I have to grade what I receive. Okay? And I think that most of the time sending by email is not going to mess up anything. I assume that's the case. But I have received papers that I know that if the person had seen that paper, they said, wait a minute, something's wrong with this. Just this summer, I got a paper from a student, and I think I know what happened. They center justified the title, and then they forgot to take that off. So the whole paper was center justified, not left justified like it should be. So, and all they had done was look at the computer screen, and you really, unless you looked very carefully, you didn't notice that. But when you printed it out, you would definitely have noticed it. And so, of course, they lost some points for sloppiness. Okay, so that's why, yeah, it's up to you. I'll take it as an email, but I have to grade what I receive. Okay, all right. Good questions. Good deal. Any other questions? Okay. So let's get going on Chapter 16, Earth and Space. And I like to call this the Earth-Moon system because we're going to spend a fair amount of the chapter talking about the moon. And sure enough, it's Earth and space, but they don't even mention moon in the title, so I sort of throw that in there. Okay. Here's the core concept, which you'll find on page 407 in your text. The way the Earth moves in space is used to define time, and we've already talked about that in many ways, and to describe location on the surface. Now, I know what they're trying to say, but that's kind of a weird way to say it. The way the Earth moves in space is used to describe location on the surface. In sort of a stretch, broad sense, I can see what they're saying. And causes other recurrent phenomena such as the seasons. Yes, for sure, how the Earth moves in space does contribute to that as well. Now here's another simulation type picture, which I guess is a reasonable facsimile. Not really, but close. If I'm understanding this well, this would be Mercury. So Mercury must be really, on this side, okay? Here's Venus here, and I don't see how they could get, no, I guess that's not Venus. That's Jupiter, because there's the great red spot. Don't see Venus on this at all. Mars seems to be back there. This, I take it as our moon, and you're on the moon taking a picture this way. That would be Jupiter, Saturn, Uranus, and Neptune. And they never would look like that. Ever, ever, ever. But it's just a rendition of it. Okay? So, unless, of course, this is Mercury, that could be Mercury, but that's way out of kilter. So I don't even see how that could be. But that's not important. Just, it's a pretty picture. Okay? And that's about it. Okay. So let's get started on the first part of the chapter, the shape and the size of Earth. That's 16.1. Either it's an oblate spheroid or it's not, but they call it very close to an oblate spheroid. Now what does that mean? That means the top part of the Earth is a little narrower and the bottom part is a little bigger, sort of like, never mind. But that's what they mean by oblate spheroid. Not quite a sphere, not a perfect sphere, but it tends to be bulge a little bit. That's what they mean, slightly pear-shaped, slightly, just very slightly. Now this makes no sense to me. A lump in the Pacific. I don't see how you can have a lump in the ocean, because it seems like if you had a lump in the ocean, the water would go down, but that's what they say, a lump in the Pacific. Maybe that means underneath, I don't know for sure what they're talking about. A depression in the Indian Ocean. Well, again, it seems like if you had a depression in the Indian Ocean, water would flow into it. It wouldn't be depressed anymore. But that's probably not exactly what we mean. Now, The elevations and depressions that they're talking about here are deviations of less than 85 meters. Now, what is approximately 85 meters? Anyone got a clue? Okay. Familiar with football, most of you, at least a little bit? Football field is 100 yards long. That would be slightly less than 100 meters long. So 85 meters would be something around 90 yards, maybe 95, almost one football field. And that would be from the highest elevation, deepest depression. When you talk about the surface of the earth, the radius of the earth is thousands of miles, then this many meters is not going to be a big deal. Not a big deal at all. Now here is this picture almost looks like it's way off from being a sphere, but it's not really. This is because, you have some of the earth in darkness here and you can't even see it. But it's a nice picture of the earth, probably taken from one of our missions into space. Someone took a picture. And what's that? That's what I was just going to say. I think I have picked out a few things on it before. I'm pretty sure that is the North Pole up here. I'm not absolutely certain of that, but I believe it is. And I think this is North America. I'm not sure of that either, but it sort of has the shape thereof. And this does look like a big expanse here, which would be the Pacific Ocean, and then the southern thing. And this does look like it could be South America here with Central America somewhere in between. But I'm doing a wild guess, okay? And you could maybe, that's the beginning of the Japanese island chain or something there. I can't say for sure. It's just a nice picture of the earth. But don't think it's that far off from being a sphere. Here's something, an illustration, that's greatly exaggerated. Greatly exaggerated. And you see that it bulges in the middle. Okay, this is what makes an oblate spheroid. And a little narrow top and bottom. Okay. And the actual sphere would be here. Now, this is greatly exaggerated because it doesn't make that big of a difference. Now, here the numbers don't quite match up. Here they're showing that the difference between and maybe they're only talking about these, elevation and depression, the difference of 85 meters, which is not very much. But even this is not. The diameter of the Earth this way is about 12,756 kilometers. This way, 12,714. That's a difference of 42 kilometers. So this is way exaggerated from 42. 42 out of 12,000 is a very small percent. Very small percent. So this is greatly exaggerated. We're closer to a sphere than this blue indicates, but we're not a perfect sphere. Okay? That's the point here. Now, in your book, there's another picture that represents the planets. Okay? And I bet you the size comparisons are probably not too off here. Seems like to me this should have been in the last chapter, not in this chapter, but they have it here. And the only thing I have a gripe about, this makes it look like Mercury is larger than Mars. Now, because Mars is in the background, and it really is. But Mercury is considerably smaller than Mars. This makes it look almost like Venus is larger than Earth because Earth is further back. But then, here's where the relative sizes are right. That's probably a good rendition of Jupiter compared to Earth. We are minuscule compared to Jupiter. Saturn, also huge, and then Uranus and Neptune, very, very big too. They even got the colors pretty close to right on that. Okay? So that one's not as bad as some of the others. But of course, they never line up like that. But they that is a better rendition, probably, of the relative sizes. That Earth, space objects in perspective that I put on the website, that probably gives the best relative size of anything I know. Okay? Darren came in, and Zachary came in. Okay? Anybody else come in that last group? I don't see it. Okay. So, moving on, there's another fairly decent figure, and this is actually one that's a lot closer to reality. I don't know if this is an actual shot of the night sky or if this is a planetarium. It looks sort of like a planetarium, but it could be an actual shot of the night sky in some place that has very few clouds and no light to break it up. Because all the planets are pretty close to being on the ecliptic of the sun, because we're all in a disk there, so Pluto wouldn't have been, but you'll see some of the planets here, and that's why I think this may actually be a shot. Here's Mercury here, and I'll never have seen Mercury that distinct, so that's why I think it may be a planetarium shot. I don't see Venus on this one, so it must not have been out of sight, so it could actually be a night. Jupiter's here, Mars is there, Saturn there, and those are the planets that show up on this particular night. They're almost in the same plane as the sun. Awfully close. There's a few stars that are in that same plane. Here's Regulus here, Spica here, and then Antares here, a little bit off of that. Those are some fairly bright stars that would show up too. Now, I can't believe this is a actual night sky. It could be, because Saturn, I guess you could see that way, but it's going to be pretty tough. And Mercury, that's the one that leads me to think this may be a planetarium where they sort of put it in there. All right. Again, it fits okay in this chapter, but I think it would have fit better in the last chapter. All right, moving off that page to the next page, we're now into 16.2, which are the motions of the Earth. And the top figure there is the same one we saw here, okay? Same one, and that, of course, is a NASA shot, and then the same figure 16.4 that we have in our book is the same one here. All right, now let's look at the motions of the Earth. Now, we already said in our core concept, the motions of the Earth define certain things about it. 3 of the motions of the Earth are completely independent of the motions of the Sun and the galaxy. So they have nothing to do with the motion of the Sun, nothing to do with the motion of the galaxy, or within the galaxy. These are just specific motions of the Earth. And the first of these, I don't know why they list this first, annually we go around the Sun. Okay, we make that long, long voyage and go all the way around the Sun and get back where we started about 12 months later. Okay, that's our yearly revolution around the Sun. That determines our year, of course. Okay, now we're also spinning. As we're moving around the Sun, spinning much more rapidly, we rotate every 24 hours, approximately. Okay? And we rotate about our axis, and that's what makes it look like everything is going around us. It really isn't. We're spinning, and the background that's stable seems to be turning. Now this next one is this happens 24 hours, once every day. This happens once every year. This happens once every something like 1,700 years or 17,000 years. It's a long time. It's a clockwise wobble of the Earth's rotation axis. Now, that sounds bizarre, and no one plays with these anymore, but have you ever played with a top? You put in wind the string around it, do it, and then it spins like crazy there. Okay? When it's spinning really fast, it's almost perfectly level. But when it becomes to slow down a little bit, you start seeing this kind of motion. That's precession. And the Earth precesses ever so slowly and slightly. We'll talk about that a little bit later, give more detail on it. But that has nothing to do with the sun, nothing to do with the galaxy. That's just motion of the Earth. These two, once a year, once a day, once every 17,000 years or something like that. It's just way, way, way not noticeable, okay, in the short term. So let's look at the specific ways that it moves through space. Now, some of these are included on the previous slide. Some of them are brand new here. First one, daily rotation at about 1,670 kilometers per hour. Okay, that would be about 900 miles per hour, close to 1,000 miles per hour at the equator. That's how fast people that are on the equator are moving around the Earth. That seems like it would be dizzying, except the Earth is so big, of course, you don't even notice it. That's the daily rotation, a pretty rapid rotation at the equator. Of course, at the poles, you're just spinning like this. You're not going really all that fast. Okay? At the equator, you're doing spinning just that fast, but you've got a lot bigger distance to cover. Now, we also have a monthly rotation about the Earth-Moon center of mass. We'll talk about this more in the last part of the chapter. But you see, our moon is so big compared to us. Okay? I mean, we're much bigger than the moon. But we have the biggest moon-to-Earth ratio of any moon in the solar system. Certainly, Jupiter has at least 4 moons way bigger than Earth's moon. And Saturn has at least 1 bigger than the Earth's moon. But those are huge planets, huge planets. We are sort of a small planet, and yet we have a moon that's in the same range as them. So the ratio of our moon to our own size is really big compared to anything else in the solar system. So because of that, it's not just that we sit here and the moon moves around us. When the moon moves around us, we are moving slightly because the moon's gravitational field has an influence on us as well. So there is, and that's what they talk about here, the monthly rotation about the Earth-Moon center of mass. Where is that center of mass? It's part of the Earth, okay? So we don't even move a full radius, okay, as the moon's going way around us, but we do move a little bit. Okay, the yearly rotation about the sun, that one we're going at about 106,000 kilometers per hour, which would be about 60 to 70,000 miles per hour. We are flying around the sun. But it's such a big orbit, it takes us a whole year to get there. Just gives you an idea of the size that things are. Okay? The orbit of the solar system about the center of the Milky Way galaxy. If you remember, the Milky Way is a spiral galaxy. It has a nuclear cluster of stars in the middle, and then it has these spirals going out from it. And we are about 2/3 out one of those spirals. So we're going around the center of the Milky Way galaxy, okay? And that's our whole solar system is, the sun, and it pulls all of us with it. That's going along about 370 kilometers per hour, which would be about 200,000 miles per hour. It's moving, really moving. Okay? Now, the orbital motion within the sun's local star group. Okay? Now, we talked about there being clusters of stars within a galaxy. Our sun is in a cluster of stars within the galaxy, and we're going around the center of the galaxy like this, but we're going around our local star group, which probably has a smaller, very small black hole, and we're going around that. But look at that speed, 1,000,000 kilometers an hour, which is about 600,000 miles an hour. Whoa! Okay? Now, the motion of the Milky Way galaxy relative to remote galaxies, moving further apart, remember, everything's expanding in space, and that's about 580 kilometers per hour, which is, I almost said per gallon, I thought, no, you don't be that good at math, guys, per hour. And that would be about 350 or so thousand miles per hour. Okay. So those are 6 biggies. Here are some minor motions. Changes in the shape and size of the Earth's orbit. Okay? Remember, we're not a perfect sphere. So this thing about going around the sun, we're not at a constant speed there. We're changing speeds all the way around. So when we're further from the sun, we're moving just a little bit more slowly, and when we're closer to the sun, we're moving just ever so slightly faster. So the changes in the shape and the size of the Earth's orbit. Also, and this is the one we mentioned before, that slight change in the tilt of the Earth's axis, that is slow, really slow change there. Very slow change. And then this one is interesting. Slowing of our Earth's rotation rate. We think that's happening. No one's been able, it doesn't make a measurable difference year by year, decade to decade, century to century, but over long periods of time, we are ever so slightly slowing down on our axis, rotation rate. So it may be in a few million years, our days will be 25 hours long, not 24. Yeah, I sort of making fun of that. It's a very, very slow change. Okay, those last 3 are all really, really minor. Okay? People are still writing, so I'll give you time. And by the way, I believe I have all the PowerPoints out there. So has anyone looked at Blackboard to see? I know what's that? But really? You did not? Okay, I have to check on that because I thought I got them loaded Tuesday. Yes.
Have you already graded the test?
Okay, a little louder.
Have you already graded the test?
No, I explained that earlier. I did get the labs, those that had been turned in, the Chapter 14 labs. I finally got those graded today. I don't have them on Blackboard yet. I was just at the point of starting to grade the test when I got a bunch of interruptions, so I didn't get any of the tests graded.
You supposed to turn in the labs? Oh.
I'm sorry?
I didn't know we were supposed to turn in the labs.
You didn't have to, but several people did. Okay? I said you have a week to turn in the labs, but I said if you got them finished, you can turn them in any time. So I'm guessing, let's see, just looking at it, close to half the class turned in labs and close to half of them didn't. So I got one paper turned in, and not all the people took the test, so there's several that still take the test. But I don't have those graded yet. I hope to work on that some while y'all are taking your second test today. I'll be working. The Chapter 15 test is the last 30 minutes today. We talked about that last time. And the Chapter 15 lab is the 2 hours before that. So at 3:15, stop me before 3:15 so we can get started on the lab. All right. Everybody got this now? It's a long, wordy PowerPoint, but got it. Okay. Now, let's continue with this. The overall picture from space is, okay, the Earth, of course, is spinning. The Earth, of course, is going around the Sun, but the Sun's going around the center of the Milky Way galaxy, so we're going with the Sun, so we're following sort of a corkscrew type pattern. They call it a helix, which is the better term for it. Along a helix at incredibly fast speeds. Okay? Viewed from the Earth, it looks like everything else is going around us. The ecliptic plane is the plane that the Sun travels around us. It looks like it really isn't. That's our spinning and where the Sun is above the Earth at any time. The planets move in a narrow band, and that's what the picture in the book was talking about. They're very close to the ecliptic plane. So the solar system, at least the planetary parts, are relatively flat. And the Sun moves along the ecliptic across the background stars. Now, it's not really moving, we're spinning, and that gives the perspective that the Sun is moving among the stars. It really isn't. I mean, it's moving with the stars. Okay? Here is that helix. We're going around the Sun, but the Sun's going around the center of the galaxy, so we're staying with the Sun. It looks like to me they didn't quite make the top part of these circles quite big enough, but so we're doing like this. As the Sun's moving, we're going around the Sun. So that's what makes the helix. That's what they're talking about, a helix. You can think of it as a corkscrew-like motion, okay? Because the Sun's moving this way as we're going around the Sun.
Not done.
Okay, yeah, take your time. Now, this is what we call the ecliptic plane. That's the plane that we're in with the Sun in the center. And just about all the other planets are very close to that ecliptic plane as well. The inner ones are in here, the outer ones are out here. But that's our ecliptic plane. And as we move around here, of course, the stars that are over there are always over there. And when we're over here, we see those stars. Or not, if that's daylight then. If we're over here, we see these stars because the Sun is on this side of us, okay? So as the night moves on, we're moving around the Sun, so we're seeing stars here and here and here and here. They're fixed. It's just that we're moving around the Sun, so the perspective of the stars seem to be moving. They really aren't. Not anything we could tell. And a little bit of what we'll do today in lab is really close to this too. The labs and the chapters don't exactly match up. Things we do in one lab we'll see in later. In one chapter we'll see in several labs, and things we see in a certain lab may cover 2 or 3 chapters. Okay, so there'll be a lot of overlap and interconnectedness. Yeah, they're out there. Okay, good. The PowerPoints are on Blackboard. Okay, so I hope they were. Okay, and this is just a lot of people, not a lot. Some people like to actually print off the PowerPoints and use them to take notes on. And I'm not saying you should do that, but some people do it. Now, one disadvantage of doing it, that gets a lot more passive. When you're actually writing down, that's active thought and thinking. Reading it is sort of passive. Writing it is more active. So there is an advantage to taking down things off the notes, but it is a little slower. So you decide what you want to do, how you want to invest your time and efforts. All right, to move on? Okay. So, we're going to have a revolution. No, I'm sorry. This is the revolution of the Earth around the sun. Okay? Now, the orbit defines the plane of the ecliptic. Okay? I'm going to let Ishmael be the sun. You're pretty bright, aren't you? Okay? So, we are the Earth, and we move around you like this. Okay? That plane that defines the sun and our motion, that's the ecliptic. Okay? The orbit defines that ecliptic. The ecliptic is the apparent path of the sun through the heavens as seen from Earth. The sun's sitting there. It's not moving. Earth is the one that's moving. So therefore, it seems like the sun is moving in several ways. Number one, the Earth's spinning, so the sun seems like it's rising in the east and setting in the west, but it's really our motion. But then we're also doing this, so the sun seems in a different place at any time of the year because the stars that are back there look different. So it's not moving. We're the ones doing the movement. I mean, it is moving, but nothing we could be able to see. Now, ecliptic is the plane through which, defined by the sun and us and our orbit. Elliptical orbit, that's not the same as ecliptic. What that is the orbit is not circular, but slightly off circular. It's elliptical. One axis is a little longer, the other axis is a little shorter. Whereas a circular orbit, you'd always be the same distance from the sun. Okay? Now, this is probably would be a surprise to you. We're actually closer to the sun in January than we are in July. And that seems counterintuitive, doesn't it? Okay? And it's not a big difference, okay? Well, it sounds like it is. 2.5 million kilometers closer to January and 2.5 million kilometers further out in July. Now, that's a total difference. But how far are we from the sun? 93 million miles from the sun, which is almost 600 million kilometers. So what's 2.5 million out of 600 million? A very small percent. Very, very small percent. Okay? Now, the reason we're warmer in July than we are in January is that we're tilted toward the sun. That makes a lot more difference than that 2.5 million mile difference. Now, I pity the people down in Australia and anywhere in the southern hemisphere because you see, their January is their summer, so not only are they tilted toward the sun in January, they're also closer. And in July, which is their winter, they're tilted away from the sun, but also further from the sun. So I haven't ever seen any data to support this, but I would be really interested to see if their temperature variations between summer and winter aren't greater than ours, because we are tilted toward the sun when we're further from the sun and tilted away from the sun where we're closer to the sun. So it would seem like it minimizes our temperature differences summer to winter, but maximizes theirs. Again, I haven't seen any data to support that, but it just seems like that would be the case. The thing is, that's not making a huge amount of difference. Earth receives about 6% more solar energy in January. That's the entire Earth in January than it does in July. Okay? Which it seems like to me, with that being amplified in the southern hemisphere, that seems like that would be important. But I've never seen data to support it, but I'm guessing that's the case. Okay, that's our revolution. Okay, we're going around the sun, not in a circular pattern, but in an elliptical pattern. Okay? And at different times, see, picture this, okay. Ishmael's the sun, right, guy that he is. Okay, this, say, is late August, and I see stars. I don't see the stars because he's blocking them out. But if I look at these stars back here at night, midnight, these are the stars I'm going to see. So let's go another month or two when I'm over here. Now I'm looking at these stars at night. Those are over here. The ones it seems like the sun, I'm seeing different stars. It's just because of it's nighttime, we're further from the sun. I mean, we're turned away from the sun, so we see a different set of stars. In, what was 8, 12, 20, yeah. Oh no, I'm sorry, 6. Okay, in February we'd be over there. And all the stars we saw at night over here are in the daytime, and we don't ever see them. We see those there that we'll never see in August because they're on that side of the sun. So you see, we see different stars at different times of the year because of our motion around the sun. All right, everybody got this one? I was just trying to kill time with that.
I got it.
Huh? Okay.
I got it.
So here is showing what I was just talking about. Now, again, they've exaggerated this like crazy, okay? June, we're not that much further from the sun than we are in December. They've exaggerated this, but the key is we're pointed toward the sun. Everyone in the northern hemisphere is tilted toward the sun. And on June 21st, which is, or 22nd, somewhere around there, what day do we call that? Say again? Okay, the equinoxes are these. Equal day, equal night, that's March and September.
Solstice.
Solstice, that's when the sun stands still. See, up before June 21st, okay, the sun every day got a little higher in the sky, and then on June 21st or 22nd, it stopped increasing, and then every day after that, it's a little lower in the sky. So the solstice, the sun stood still. The sun is directly overhead, 23.5 degrees north. What do we call that? That circle there? Tropic of Capricorn. Tropic of Capricorn. Cancer is in the southern hemisphere. And that's what's the sun directly overhead in December 22nd, 23rd, somewhere around there. Okay? Now, because the Earth is tilted at 23.5 degrees, when we ran into that all the time, that's what makes this 23.5 degrees north, that 23.5 degrees south. All those angles match up there. Because of that tilt, that's what gives us our seasons in the northern hemisphere or the southern hemisphere. Okay? Remember that question on the first lab about the sun being directly overhead of someplace in Egypt, started with an S.
Stonehenge?
No, that's in England, in Egypt. Syene, Egypt. Remember that Eratosthenes read and studied that the sun was directly overhead. You could see the sun at the bottom of a well, reflection of the sun. That there were absolutely no shadows at all on June 21st. And that's because the sun was directly overhead. And Syene Egypt would be really close to 23.5 degrees north. Okay, that was the question on the left. Okay, now moving on around September, which is coming up pretty soon. Equinox, equal day, equal night. The sun's directly over it's only ecliptic, of course, but it's directly over our celestial equator too. So therefore, there's exactly 12 hours of daylight, 12 hours of darkness, every location on the sun. The North Pole, the South Pole, everything in between. Exactly equal day, equal night, equinox. Okay, and here's Dimitri. Okay. Now, just a little bit catch up here. We're in chapter 16 now. We're somewhere around page 410, 411, or about 411. Yeah, I'd say we're on 411. But we only go until 3:15. So stop me before 3:15 so that we can halt there and start the lab from chapter 15. Okay? And then as soon as you finish the lab from 15, you'll have the test from 15. And that will be the last 30 minutes of the day. So if the lab goes more than 2 hours, we stop at 5:15, so you'll have at least half an hour to work on the test. Though I think we'll finish early, so you'll have more time if you need it. Okay. So, all right. Then you move on from equinox, September 22nd, 23rd, sometime there. Move on around till December. Now there, you're not the closest point to the sun, but pretty close to it. It's January, but this is late December. But we're tilted away. That's what makes us cold. Not that we're closer to the sun. That would make us warmer. But that's just minuscule, the amount that we're closer to the sun. The fact that we're tilted away. Now here's an important concept. And you see it better maybe down here. You see the North Pole is tilted away, and no matter where the Earth spins, it's never receiving any daylight at all from the sun. No direct radiation of the sun. In fact, there's a circle up here. Does anyone know what that circle is called? The Arctic Circle. On December the 22nd, 23rd, sometime there, there's no daylight. No sun, the sun doesn't come up at all anywhere north of the Arctic Circle. It's all in complete darkness. Okay? It may look like it's going to be dawn for a little while or dusk for a little while, but then it gets black again. Okay, so
that's just for 24 hours.
24 hours, yeah, for that. Now, if you're right on the Arctic Circle, the next day the sun will come up just a little while and go right back down in just a few minutes. But on that day, it never rises. It's close, but not quite there. Now, back on June 21st, 22nd, same thing's happening down here. The Antarctic Circle is down here, and the sun never rises anywhere inside the Antarctic Circle. Okay. Then you get to March 21st, 20th, 21st, somewhere in there. That's the spring or vernal equinox, 12/12, daylight darkness, everywhere on the globe. But all the time at the equator, it's 12 and 12, 12 and 12, 12 and 12, 12 and 12, because it's equal. It's equal. Okay. Now, this might help you see it better. Notice, with the tilt of the sun, 23.5 of the Earth, 23.5 degrees, sun in the center there, you see the North Pole is tilted toward that, so as the Earth spins, it never sets. You know, the sun is always shining on it. Not very directly. It's always low in the sky, but it never sets. It gets lower and then goes up, but it never goes overhead, anywhere close to it. But you have 24 hours of daylight. It's pretty dim daylight. Part of it almost seems like dawn or dusk, but it never sets. Whereas down here, that same thing is happening here in the winter solstice. It's their summer solstice, our winter. Okay? And then the equinox is there. Make sense? All right. Those two figures are on page 411. All right, now we have rotation as well. Rotation and the Earth's axis. I don't know why they say it that way, but the Earth's rotation axis is inclined 23.5 degrees, as shown, so let's show it. It's been on every slide so far. Okay? This is the Earth down here, tilted at 23.5 degrees. That tilts our celestial sphere that way too, with the North Star being there directly over our North Pole, and it sits there. We spin, it sits right where it is. All the other stars seem to go around it. Now, the sun is out here somewhere. This is the ecliptic. That's the plane where the sun is. Here is our celestial equator. Notice they're tilted from each other. How much? 23.5 degrees, always, okay? At the spring equinox, the sun is directly overhead the celestial equator, on the celestial equator. So you have equal day, equal night. Into the summer, the sun is above the, this is winter, okay. This is the celestial equator. The sun is below, in the winter equinox, below the celestial equator by 23.5 degrees on December 21st, and above the celestial equator by 23.5 degrees in the summer solstice. Somewhere in between all the rest of the time. In spring and summer, the sun is up here. Autumn and winter, the sun is down there. Okay. The seasons, they're determined by the orientation of that rotation axis. So here we are in late August. We're almost at equinox. Not quite. That'll be not so late in September, but 3 weeks into September. So we're getting close to equinox. At equinox, the sun is directly on our celestial equator. Directly on it. Equal day, equal night, 12-12, everywhere on the planet. North Pole, South Pole, equator, everywhere. Okay. After that, we move on around here. Northern hemispheres, our days are getting shorter, the nights are getting longer. We calculated that in the last lab. And we're moving toward winter solstice. At that time, the sun is as low in the sky as it ever gets. Okay? And at that point, we have the least radiation coming in to us in the northern hemisphere. Southern hemisphere has most, but because in January we are just past winter solstice, and we are closest to the sun, so that sort of moderates maybe just a hair. But in the southern hemisphere, that would be, actually seems like it would be making the summers even hotter. Okay. Yes?
So in the southern hemisphere, it would be considered like that summer, right?
A little bit longer.
In the southern hemisphere, when it's like, I guess winter for us, they would consider summer.
Summer for them, yeah. And the sun's up longer for them, shorter for us, because we're tilted away, they're tilted toward. Yeah. So, yeah, that's their December, Christmas is in almost the peak of their summer. It's a few days after the maximum height of the sun. So yeah, it's on the beach on Christmas Day. Okay.
Does the time change have to do with anything?
Okay, the time changes?
Yeah.
Okay, yes, because, see, right here, let's say, okay, what is it? About 2 o'clock, let's say. 2 o'clock, we're just past high noon, but on the eastern, they're at 3 o'clock. In Mountain, they're at 1 o'clock, and at California time, they're at noon. Okay, so yeah, but that hasn't got to do with tilt. It's just that the spinning of the Earth, every 15 degrees, you move another hour, okay, in the process. So, and we did that in the last lab too. 15 degrees of arc was 1 hour, I think that was of right ascension. So, yeah, that's where that comes in. Now, the thing about daylight saving time, that's just a man-made thing so the bankers can golf later. I don't know. I just made that up. But that's what my opinion. They all blame it on the farmers. I don't think the farmers really want to change it. The cows are going to want to be milked at the same time of day, whether you're on daylight saving time or not, and you have to just get up an hour earlier to milk them. So I don't think that is fair to do. Okay. All right. We talked about the seasons, winter solstice, spring, we talked about all that. The celestial equator is the line on the celestial sphere above the Earth's equator. Yeah, we talked about that, so I think we got that knocked. Okay to move? All right. So I'm thinking we're moving to approximately page 412. All right. Now, this is an interesting question, but before we get there, there's a couple of examples. What is the latitude of an observer who measures the sun's altitude of 38.5 degrees above the southern horizon at noon on the summer solstice? Okay? We know where the sun is relative to the celestial equator. It's at, well, plus 23.5 degrees. Okay? So what you do is add that 23.5 degrees to the 38 degrees, and that tells you your latitude for that. So you can go and play with that. We did it in the first lab. They're asking these questions in sort of backward form, so you have to sort of think backwards on them. So let's move on to rotation. That's the bottom part of the first column on page 412. Now, strange question. Does the Earth really rotate? Sure doesn't feel like we're spinning. Does it really rotate? We have 3 pieces of evidence, at least, that indicate yes, it is. Okay? Now, Galileo, this is what convinced him that Copernicus' model, the heliocentric model, probably was correct. When he looked through that new improved telescope that he built, and he could see Jupiter and see that it was really spinning, he said, well, if Jupiter's spinning, why isn't the Earth? Sure, it's spinning, therefore the heliocentric model made sense. Now, I don't suggest that you do this, but people who have the right filters and other things can look at the sun and determine that the sun is spinning too. Okay? What's that? No, I never look at the sun with the naked eye. Okay? You can look at pictures of the sun taken at different times of day, and you'll see it is moving, or especially different days of the week or weeks of the month or something like that. Take a series of pictures and you can see that the sun is indeed spinning. Most of the other planets, we don't have the detail to tell that, but certainly Jupiter and the sun. We know the others are spinning also. Now, does anyone know what a Foucault pendulum is? Have any of you ever been to the McWane Science Center? Okay. And I don't know if they still have it there. They did have a big pendulum suspended from the ceiling that made a big arc like this. Just it was always moving like this. Okay? If you went there morning, noon, and night, you would see that that arc has changed direction. That's a Foucault pendulum. The pendulum oscillates in a fixed direction. The orientation changes as the Earth rotates. Now, the example they give of this, and we could try to do it, but I think it's better to imagine it. Okay? Let's imagine a ring stand here, and you've got a I don't like the way it is. Let's just say that ball is suspended from it. It's not hung over it. It's suspended from that. That's what I think they really mean. Okay? Say somewhere out here at the end of this. And you got this on a stool. And you spin this, you start the ball going back and forth like that. And as long as the stool is in the same place, it's going back and forth like this. But if you spin the spool, then it's going like this. And that's exactly what a Foucault pendulum does, suspended from a high ceiling. It actually, you can mark it as the hours roll on. You can mark those hours on how it changes its rotation. So it oscillates in a fixed direction. The orientation changes as the Earth rotates, because just like the spool still spinning, the Earth is spinning. Now, there's one other piece of evidence, and that's the Coriolis effect. Pretty sure he was an Italian scientist. I can't say for sure, but I believe he was. But the name sounds like it. And that's the deflection of paths as Earth rotates beneath moving objects. Okay? Quite a statement there. Deflection of paths. I don't know if any of you are big World War II fans, or any war fans, but some people like history and stuff. And there were some of the bombers that flew missions over Europe especially, that flew at really high altitudes, dropping the bombs on the various German and maybe Italian targets. But if they were looking out and said, there's Dresden, let's drop the bomb. By the time the bomb landed, it's missing Dresden. Okay? Because the Earth is spinning under it. That's part of what we call the Coriolis effect. There's actually more to it than that, because when an object falls and the Earth is spinning, it sort of gives it a torque. So it also deflects in a different way too. Frankly, you see that in weather patterns. We'll talk about this in a much later chapter, next to the last chapter. When you have what they call falling weather, low pressure, so the particles or whatever, the winds and stuff, are moving downward as the Earth spins, you get rotation in one direction. Whereas if it's high pressure and things are moving up, then you get rotation in the opposite direction. Now, I bet you every one of you have seen this before. If you have a sink full of water, or a tub full of water, even a toilet bowl full of water, and you pull the plug on the sink or the tub, does the water just go straight down? No, it spins because of the Coriolis. That is showing the Earth is spinning. Now, if you were sitting right above the equator, that's what it would do. The water would just go down the hole without any spin to it. The further north you are, the more spin it is. Okay? That's the Coriolis effect. Okay? And, weather patterns. Low pressure spins counterclockwise and high pressure clockwise. I believe that's correct. In the northern hemisphere. When you go to the southern hemisphere, they reverse. Because the Coriolis force. The torque is different.
So is that like there's inflection forward in different places?
Yeah.
Different directions?
Yeah. North to south of the equator. In fact, just to show how weird physicists can be, I had one professor at Georgia Tech for at least 2 courses. I remember 2 that I had him for. He was a nice-seeming guy. When he got off into his specialty, though, he was hard to follow because he ate that stuff up, and that was crystallography. Okay? I mean, he knew that stuff inside out, and I think he thought it was intuitively obvious to anybody. It really wasn't. Okay? In our general physics course, he was pretty good because he just taught it as anyone would teach it. Okay? So, being a honcho in crystallography, he was actually the chief editor of one of the big international crystallography journals. He was that honcho, up there. And they had their international meeting one year in Rio de Janeiro, which is in Brazil. and that's one of the party cities of the Southern Hemisphere. Okay, Rio, Sao Paulo, Brazil is a big, even bigger, but it's a business center. You know, everybody's serious and works hard and stuff like this. In Rio, everybody parties, okay? Lots, okay? So, anyway, their meeting was in Rio de Janeiro, Brazil, Southern Hemisphere. So he got to go to this meeting because he was the editor of the journal and that kind of stuff. And he was so excited when he got there. And he just could not wait until he got to his room, and he threw down his bags and rushed to the bathroom to flush the toilet and watch the water go down in the opposite direction. Now that's the physicist, party city of the Southern Hemisphere, and he rushes in to flush the toilet. Okay, yeah, right, okay. And it did spin the opposite direction, okay. We got sort of tickled at him telling us that and being so excited about it. Okay, that's Coriolis effect. Now, that other really minor motion, this is precession, okay? It's a, when I say slow wobble, it is a slow wobble. I mean, really slow. I was even missing it on the years. 26,000 years for it to go one circle around that precession. 26,000 years. I won't be around then, okay? No one I know will. It's a reaction of the Earth to the gravitational pull on its equatorial bulge by the moon and the sun, both pulling, that makes us wobble just a little bit. 26,000 years for it to go through one cycle of that. It changes the direction of the rotation axis on the celestial sphere, because guess what? Polaris has not always been our North Star. Ever since mankind has looked at Polaris, it has been, because we've only been around, what? Civilization, let's see, it's now 2018. In 1018, we were navigating some, but not very much. In 0018, Jesus was alive, okay? In so let's see, what am I doing? I didn't quite say that right. 26,000 years, okay? I was just counting back. I've only counted back 2,000 years then. Out of 26,000, that's nothing. Polaris was up there then, you know. Very little change in that time. That's 1/13 of the thing. 2,000 years, 1/13. Okay. The position of the equinoxes in the zodiac, they change ever so slightly. So, back when they first came up with these, I think that was Babylonians or Sumerians or somebody came up with the zodiac, and that was probably a few hundred, maybe even 1,000 years BC. So about 3,000 years ago. They were on the ecliptic, but guess what? Over time, some of them have inched off the ecliptic. There's actually some constellations that would be more suited to be that. But since they don't mean anything anyway, and we still call them by the old names, Leo and Virgo and Capricorn and Sagittarius and all those. Those are just naming the constellations that are close to the ecliptic at those times. Okay? I'm going to flip this, but it's not going to change the wording any. It's just going to show this. This is what I was talking about before. A top, when you spin it, it precesses about the axis. This is greatly exaggerated. That top's getting ready to fall. But at the very beginning, it precesses just a little bit. Okay, but then the slower it goes, it precesses more. So this one's just about ready to fall and stop. Okay? Well, just as that happens, the Earth precesses ever so slowly, once every 26,000 years. So about AD 14,000, that's in the future, Vega will be our North Star. Okay? 14,000? Okay, we're at 2,000. We got a long way to go, folks. That's not going to happen in anyone's lifetime here. We may not even be around then, okay, if we keep going like we're doing. So right now we're probably right about, today it's here. In 1,000 years it might be here and then here. So it could be after a long, long time. There won't be a real Polaris. It'll be some really faint little star. And then later it may get, Vega is a pretty bright star. In 14,000 years, or 12,000 years now, that will be our North Star. Everybody will think, well, we've always had a bright North Star, however, not really. All right. Everybody got it? Anyone need it any longer? Okay. Now, okay, I'm sorry. Let's go back. If you remember, don't get burned out of place quite yet. I'm going back a little bit. Remember on this slide when we said the sun rotates? If you look at the picture on page 412, it's not shown on the slide set, but the sun's spinning motion can be measured by carefully monitoring the changing positions of sunspots. They aren't moving. It's the sun that's moving, spinning on its axis, and that's what makes them appear to move. And so that's the evidence for the sun spinning. Don't look at the sun and try to see it. You're going to burn your retinas up, you know. But these are from pictures. Okay. So now we're ready for place and time. All right. We've already been talking about this lots and lots and lots. So here, I'm going to sort of put them all together. The Earth's periodic motions provide a basis for determining place and time. Now, you might say, how does place? Time makes sense. How does place enter the picture? Well, if you think about it, we have a North Pole and a South Pole. Okay? We spin about that. So that fixes 2 points in place. And then you take the line that's equal distance between those all around the globe. That fixes the equator. Okay? So sure enough, that helps us determine where we are. The first measurement you give on where you are is your latitude. How far north or south of the equator do you live? So that is determined by the axis through which the Earth spins. That's part of our periodic motion. Okay? Now, there are other things too. Rotation provides an axis of rotation. That's a strange sounding sentence. Useful for determining locations on the globe. That's it exactly. It gives the poles, that gives the equator, and then you measure how far north or south of the equator, and that gives you part of the location of where you are. So that rotation provides the axis. The axis identifies north and south. It identifies the equator. And then from there you can measure how far north or south you are of the equator. Now, the combination of rotation and revolution determine the cycles that we can use for time standards. Right. Now, we'll see in, is it today's lab or next lab? I don't remember which. There are several ways you can measure a day. Okay? The average comes out to being 24 hours. Not all days, depending on how you measure it, are exactly 24 hours. That's what we use as the average. Okay? And that's based on rotation. But you see, not just rotation, because when we're spinning, we're also moving around the sun. This is a fast motion, that's a slow motion, but they're still building together. We'll talk about that some in today's lab. So the combination of the two determine the time standards, and Stechnia was, I messed it up really bad then, was asking about time zones. They very much come into play because of that, the rotation and revolution about the sun. Okay? So time, big important. Okay? For instance, rotation of the Earth, basically with a little bit of revolution, determines our day length, right? Revolution around the sun, that gives us our years. What you reckon gives us our months? Say again?
Rotation.
Okay, well,
Rotation.
rotate. Well, something else. Look at the term month. Take the first three letters, and what celestial body do you almost see in that? The moon, exactly. The moon and its motion around the Earth defines our month. Our seasons are defined by the combination of basically our revolution around the sun and the fact that we're tilted. That gives us our seasons. So you see all forms of time. Hours of the day, rotation with a little bit of revolution. Length of a year, revolution. Okay? The month, revolution of the moon around the Earth, approximately anyway. So all those are used. Oh, trying to think if there's anything special about weeks. I don't think so. It's just how we decided to split it up. And I bet you most of it came from Genesis, okay? 7 days. That's what defined that. So there's nothing place time that determine the weeks. The months, yes. Okay? Everybody got it now? So let's identify place. All right. There's actually, believe it or not, still a society. It's sort of a joke. But there is a society that's called the Flat Earth Society. They pretend they really think the Earth is still flat. Huh? B-O-B? What does that stand for? Okay. We know it's not. I think they know it's not either. But if we did live on a flat planet, then you could identify any place on that by an X coordinate, Y coordinate, or anything such as that, and you can pick any point and identify it. We don't live on a flat surface. So if we did, intersection of two straight lines would form our location, like a page on a book. Say how far you are from the top of the book, how far you are from the center of the book. You know exactly where on the page you are, without a doubt. Okay? But we live on a sphere or a oblate spheroid, and it's a lot harder to give a location there. So we need some things to identify to help us figure out where we are on that sphere. Okay? So the first of these is, like I said before, we have our two poles fixed by the axis, and we have the line directly in between those called our equator, equal distance from that. So from our equator, which we will classify as 0 degrees, we'll go, the North Pole will be 90 degrees north, South Pole is 90 degrees south. Okay? So what we do, we split that 90 degrees into 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay? Now they show here 20, 40, 60, 80, 90. Actually, the best way to do is 15. 15, 30, 35, 45, 60, 90. Okay? That, I left off one. 75, 90. Okay? That evens it out some. Okay? However you do it is how far, if you were in the center of the Earth, which you wouldn't be, you'd burn up to a crisp, but if you were there, what would the angle from the center of the Earth and the equator, what angle is that defined? And that's your latitudes. Okay? We also call them parallel because each one of those circles is parallel to the one below it. They never cross. Now, notice those circles get smaller as you go up and get smaller as you go down. There's only one of those which we call exactly circumnavigates the globe, and that's the equator. We call that a great circle. Great circle because it exactly goes, if you were to slice through there, you'd be right through the center of the earth. You slice through here, you'd be north of center. You go through this axis, but you wouldn't be at the center. And the further north you go, the smaller and smaller those are. Okay? So that's the first way. Identifying place, we need to know how many degrees you are north or south of the equator. Now, in a lab coming up, like 2, 3, 4 labs from now, more than 2, we're going to do latitude and longitude. It would fit really nicely here, but we got other things that fit even better here, so we'll do that one later. So hang on to this. You're not through with this just when we finish this chapter. All right, and here's the way you measure that. You pretend you're at the center of the earth. You've got a big protractor there, and you're measuring how many degrees you are from 0 at the equator to 90 degrees due north, North Pole. And you just break that up. They show 20, 40, 60, yeah, and so on. That's the first way you identify. But that only gives you a north-south distance or measure. You need something else. And I don't know what happened. All right. Now, let me make sure I didn't miss a slide. Nope, I don't think so. Oh, wait, there was a slide missing. Okay. I thought there was. Okay, the other thing that we measure is how far east or west you are from something. Well, equator is a pretty definite thing. Anyone can figure out where the equator is. But east and west, there's no pole, there's no fixed place, there's no equator, there's nothing that you can determine east-west. So someone had to arbitrarily pick a thing and say that's where we're going to measure from. And since who was the queen of the oceans back early in Western civilization history, when she defeated the Spanish Armada, she became queen of the ocean. What country? Huh? Great Britain. England. Okay? Sir Francis Drake. Queen Elizabeth I, they, Great Britain ruled the ocean, basically. The British Empire spanned the globe. The saying was, the sun never sets on the Union Jack. There's someplace, somewhere in the globe, it's always under the sun. Okay? Well, she was honcho on the sea, and most of the navigation and stuff was based on sea navigation. So they happened to pick Sea Navigation Britain, the Royal Naval Observatory in Greenwich, England. That's where they decided, let's make that our 0 longitude line. That was called the prime meridian, the first meridian. The number, and it's not first, it's the 0 meridian. So there it is. Find London, England, go just east of that, and there's the 0 degrees longitude. The prime meridian, okay? Greenwich, going right through Greenwich, England, okay? Now, just a little story about the Royal Observatory. My wife, it's a long, convoluted story, had some professional meetings scheduled for Paris, I think it was. So she asked one of her nieces, who was going to be out of school at that time, it must have been in the summertime, I believe it was, if she wanted to go with her. She certainly did. But when she found that out, the grandmother wanted to go. Karen's mom wanted to go. If Julie was going, she wanted to go. Well, the other niece, that was her brother's daughter, the other niece, who was much younger, well, she wanted to go too. And then as she was going, Karen's sister, her mother, wanted to go. So all of a sudden, Karen had a whole pack of them going. So finally she said, forget about the meetings, I'll just take them to Europe. I mean, they paid their way, but Karen sort of organized the trip. So they went to Paris. I can't remember which order. But they were in England for a while, and they were in Paris for a while, in London for a while. And when they were in London, they happened to have a tour that was going to take them to the Royal Naval Observatory. And that's a pretty famous place, so they took the tour to go there. And when they got there, they found the crowds of people were just amazing. And there was a big buzz going on. And he said, what in the world is happening? Well, don't you know? See, the Royal Naval Observatory is sometimes building new buildings and stuff like that. They had built a new building. And because it's Royal Naval Observatory, the Queen was coming to christen the building that day. So Karen and her mom and sisters and nieces got to see the Queen drive by and wave her hand. You know, of course, they were just part of a huge crowd there, but she got to see the Queen that day. Okay. So anyway, dumb story about the Naval Observatory. That's where the zero meridian line is. The prime meridian, right there, 0 degrees. Right there is Greenwich, England, somewhere right up there. Okay.
So she could be somewhere on the Earth and be like,
What's that?
Your location if you're on the equator and the prime meridian be 0.
You would be 0, 0. Yeah, exactly. If you're on the equator, 0 north or south, and 0 east or west, right there. Now, I don't know that there's anything special there. There's where it is. Just out in the middle, or not in the middle, of the edge of the South Atlantic Ocean. Okay, nothing there. No island, nothing, but you're 0, 0. You're a big 0, that 0 there. Okay. So, you can go so many degrees east or so many degrees west. So how many degrees can you go? 90 just gets you a quarter way around. 180 gets you halfway around. And then 90 to 180 this way. So opposite the prime meridian is another one back there, 180 degrees. So you're 10, 20, 30, 40, 50, 60, 70, 80, 90 east, or 10, 20, 30, 40, up to 180 or 170 west. And then you find. Now this is really, I guess that's okay. The scale is pretty lousy here. This is showing 30 degrees here and 60 degrees there. Not very good. East or west. We are west of the prime meridian. Africa, or a lot of Africa, Asia is east of the prime meridian. Okay. So now we have our two. Before we had X and Y axis, now we have north or south latitude, east or west longitude. You can tell exactly where you are at any place using those measures. Okay. Now, the intersection of the parallels, which measure latitude, okay, how far north or south you are of the equator, and the meridians, which measure how far east or west you are from the prime meridian at Greenwich, England, defined with respect to the rotation axis. The parallels are the latitude, north or south. The meridians are longitude, east or west. Latitudes only go plus or minus 90. Meridians go plus or minus 180. Now, here's something different about the meridians. The meridians, notice, the prime meridian, right here, it goes through the North Pole, and it goes through the South Pole. And it comes back around at 180 and goes from the South Pole to the North Pole. But every other meridian does the same thing. They all pass through both poles. They got to. And so all of them are great circles. Your latitude lines, only the equator is a great circle. The rest are smaller. But the longitude are all great circles. Just a little bizarre thing. Okay? I think that'll stay up there. So here again, another picture. The equator is 0 degrees, north or south, And then as you go north, it's 10, 20, 30, 15, whatever. North of the equator, those are your parallels measuring latitude. And south of the equator are the parallels measuring latitude south. So you have north, south. Okay? Whereas, and this is another picture, just like one we saw before, if you had a protractor in the center, that's what you would be measuring. And then the longitude lines, these are your meridians passing through north and south poles. So every one of those is a great circle, and you're 0 to 180 east and 0 to 180 west. They show every 20 here, at least part of the way. This would be 90 east, and that would be 90 west. On the back half, you get the rest of them. Okay. Now that does produce, everybody got it? That does produce an interesting place on the, oh, and here's those meridians going east or west. We've shown all these before, now we're showing them again, so nothing new here. Okay? All right. Now,
do we have to write this down?
what? It's up to you. We've already talked about these, and so we're just doing. We didn't call them parallels before; we just call them degrees. But these special parallels are climate related, and we'll talk about these again in chapter 23. Okay. And these are the ones, and we've seen this picture in different ways before. These are the ones defined by a combination of the tilt of the Earth and the location of the sun. Okay? Of course, the equator is midway between the poles. Okay? That's fixed just by the geometry of things. Okay? But then where the sun is, at the maximum, what we call summer solstice, when the tilt of the Earth is the North Pole is tilted as far as it will ever be toward the sun. That's the summer solstice. At that place here, what line does that identify here? I said them backwards, sorry. It's actually, I think you had them right. Tropic of Cancer is north, Tropic of Capricorn is south. I think you were saying it right, and I said it backwards. Okay. I can't remember that. But that's where the sun is directly overhead on summer solstice. And on winter solstice, directly overhead the Tropic of Capricorn. 23.5 degrees north here, 23.5 degrees south here. Okay. But at the same time, at the summer solstice, where the sun never sets, inside that is the Arctic Circle. The Arctic Circle is that circle there. That's a special parallel. And that's at, I think it's 66.5 degrees north, and the Antarctic Circle is 66.5 degrees south. What you do is subtract. Okay, let me get my pen set up. Okay, don't let me get past it. Okay. If you had 90 degrees, which I'm going to call it 89 degrees, 60 minutes, subtract from that 23 degrees, 30 minutes. That's 23.5 degrees. That's your tilt of the Earth at minutes. Okay? Subtract that, and sure enough, you get 66 degrees, 30 minutes. That is your north is the Arctic Circle, south is the Antarctic Circle. And inside that, on summer solstice, everything is 24 hours of daylight. And summer solstice for us, in the Antarctic Circle, everything is 24 hours of darkness. Flip them around and get winter solstice for us, everything on the North Pole, 23.5 degrees, 66.5 degrees north and above, 24 hours of darkness, whereas down here, our winter solstice, their summer solstice, the 66.5 degrees south, the Antarctic Circle, everything is 24 hours of daylight. So that's why they say they're climate related. We've talked about them many times before. Everything in between these are called the tropics because they're inside the tropic lines. Okay? Sun is always directly overhead somewhere inside this tropic at noon every day of the year. Never, ever directly overhead above 23.5 degrees or below 23.5 degrees south. Okay? Up here, 24 hours of darkness of daylight in summer solstice. Above the Arctic Circle, 24 hours of darkness at that time, same time, below the Antarctic Circle. And we flip the solstices around, 24 hours of darkness above the Arctic Circle, 24 hours of daylight below the Antarctic Circle. So those are very much climate related. Warm, hot climates in this band, cold, cold climates in that band, and moderate climates in the bands in between. And we live in the bands in between, called the temperate regions. So those are climate-related parallels. Okay? Got it?
Got it.
Okay. So, measuring time. And this is getting more toward what I have to look at it. And Stexany was suggesting, okay, measuring time. This is about page 415, right-hand column. The time standards depend on measuring intervals between evenly spaced periodic events. Blah, 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 okay? What does that mean? Okay? Astronomical examples, the rotation of the Earth on its axis, revolution of the Earth around the Sun, these are the things that determine our days, our months, our seasons, and our years. Actually, the month is more determined by the moon's motion, but we'll have to get away with that. Different ways to measure the days, month, and year. Those are the ones on spinning, the rotation, and the revolution. There are different ways, okay? And this is going to introduce you to them. And more of our lab today is going to go into this. What's that?
Can we go back here?
Oh, I'm sorry. Okay. I thought you were saying it's already past lab time. Ooh, that didn't happen, did it? Okay. So, rotation of the Earth mostly determines our day length. Not totally, because a little bit of revolution determines that too. Our revolution determines almost exclusively our year length, and the combination of the tilt and the motion around the revolution, that determines our seasons. Okay? The months are largely determined by the moon, month, moon. So that doesn't really figure into where we're talking about now. We'll talk about that later in the chapter. Okay. Now, why would there be different ways to measure days, months, and years? Depends on what your reference is. That's what it comes down to. And we'll go into that in the next few slides and really go into it in the lab today, I believe. Or maybe that's the next lab. We'll see. Yeah, it's today's lab, I'm pretty sure. Even though the lab we're going to do today is mostly from the last chapter, some of the stuff that we're doing in it, really pertains to this chapter. And a few of the things in it will pertain to the next chapter. So, chapter 16. Oh, no, that's what we're in now. Okay. So it's just all over the place. Everybody got it now? Okay. What's that? Oh, you're still writing. Okay. That's all right. Take your time. All right. Now, what would be some of the different things you could look at for your basis of a day? The sun. That is the obvious one, and that's the one we mostly use. Okay? However, you could look at the stars as well. And when a star is a certain place, and then the next day when it's that same place, that could be a measure of your day. And that's going to differ a little bit from the sun, because you see, our spinning wouldn't matter those would be the same length. But in addition to spinning, we're going around the sun. So the sun is here. The stars are fixed. So the sun seems like it's moving. It really isn't. We are. So that creates a little bit of a difference. And that's what we're going to talk about in today's lab and right now. So daily time. This depends on the Earth-Sun motion. Part of that motion is the spinning of the Earth. That's most of it. But a little bit depends on our moving around the sun. So, if you were look down on the Earth from above the North Pole, if you're out there in space, directly above the North Pole, the Earth revolves counterclockwise. Okay? Counterclockwise about the sun. It rotates around the sun. It revolves counterclockwise around the sun. It also rotates counterclockwise relative to the sun. Okay? If you're looking from the South Pole, it would be the opposite. They would be clockwise. Okay. On Earth, it looks like the sun rises in the east and sets in the west. That means we're spinning in that direction, so the sun looks like it comes up in the east and goes down in the west. Okay? It's because we're spinning there. Yeah. Well, I think the next slide is not going to change the wording any. Okay, here's what we're talking about, and this is why there's a difference. Okay? If one day we're here, we're spinning, and we're right here, and the sun is high noon, directly overhead, right here. Okay? We're going to spin one time, right? We spin one time, but while we're spinning, we move a little ways around. This is a gross exaggeration here. We don't really move that much, but for illustrative purposes, we're going to do it. We spin and move 1/365th of the way around the sun. So we move a little bit that way. Well, then, exactly one day later, the sun is not directly overhead. If we were here and one spin later, we would be right here, but the sun would be down here. So we have to spin just a little bit more in order to get the sun directly overhead. So that's where a little bit of difference. If we were basing it on a star, that star would be there, that star would be there, it would be one spin later. As it is, we base it on the sun, which is one spin plus a little bit. So that little bit is accounted for by the revolution of the Earth around the sun. Okay? Everybody got it now? No, still somebody writing. Okay? Now. Okay? So we name these days different things. Okay? The sun's motion across the sky, that's what we determine our days by. Or at least our average days by. Not exact, but average. Okay? So what we call noon is the time at which the sun crosses our celestial meridian. Okay? Our celestial meridian, if you remember, if you face due north, directly overhead through our zenith, to due south, that's our local meridian, our celestial meridian. When the sun crosses that, we say transits that, peaks right there. That's the highest point the sun will be that day, wherever it is. It's the highest point, and it's going to be rising before that, setting after that. That's local apparent noon. This book calls it apparent local noon. In the Navy, we called it local apparent noon, LAN. But the book calls it apparent local noon, ALN. Whatever. Okay. Right where we are, that's what it is. If you wait till that same event happens the next day, that's what we call a solar day, based on the sun. The apparent local solar time is given by the position of the sun in the sky at that day. Okay? It can be measured with a gnomon, is one way to say it, or commonly a sundial. It's not the time shown on clocks, except very rarely it will be. Okay? The reason for that we are here in Vesper. Over in Birmingham, it's off a little bit because they're a little further east. Atlanta will be even further east. In fact, that's a whole hour, but it's not an hour's difference, okay? So yeah, you go over to Meridian, Mississippi, and it's quite a bit later. Tuscaloosa, a little bit later, okay? So yeah, we can't all use our local apparent noon, okay? So what we do is take the average over a whole year, the mean solar time between noon, 365 days a year, average, and there's two effects that go into that. If you remember, we don't live in a circular orbit. It's a slightly elliptical orbit, meaning sometimes we're a little further from the sun, sometimes we're closer. When we're further, we move more slowly. When we're closer, we move more rapidly. So that means the Earth's orbital speed changes throughout the elliptical orbit. When we're closest to the sun, that's going to be in January. We're moving faster than when we're further from the sun in July. Okay? Not much, but a little bit.
Is that why the days are longer?
No, that's because of the our tilt. That's mostly our tilt. It does contribute a little bit, but not that much. The equator is inclined to the ecliptic, so that's what makes the day length difference. Okay? And of course, that's everywhere. So the mean solar day is a 24-hour average of mean solar time. Okay? You average that over 365 days, and you get there. Okay. Y'all are still writing? Okay. So, we have a little sundial in one of the sort of areas of a garden type area in our yard, but it just gets banged around so much. It never, you need it facing that line that's due north or due south, and then you see the shadow of it, but it just gets banged around, so you never know even if it's set up right. So most of the time, no one uses that. But way back in time, that was the best they had. Of course, cloudy days, you couldn't tell what time it is. Nighttime, you couldn't tell what time it is. There's no shadow then. So that made sundials not particularly effective. In a place that has mostly sun most of the time in the day, it wasn't a bad timekeeper. Except wintertime, shorter number of daylight hours, and summertime, longer number of daylight hours. Huh? 9 minutes. I'm thinking this may be our last slide. I want to see what the next slide is, so I'll know where to start next time. Because I'd like to give y'all time for maybe a 5-minute break if you want to take it. Y'all feel like it'd be okay?
Yeah.
Okay, so it's probably not the best place to do a break. I mean, to break the chapter, but it'll do. There is a picture of a sundial, or gnomon, as they call it, on page 416. And by the way, if you had ever wondered where they got the names for the days of the week, of course, Sunday is the day of the sun. Monday is day of the moon. It has nothing to do with it. Tuesday is based on one of the names for Mars. Okay, I think it was actually the Germanic god of the fire and war and stuff like that was Tues or something like that. Wednesday, the day of Mercury. Hard to see that, but that was some other language. Thursday, day of Jupiter. I would have thought Thor, but you know, it's Jupiter, I guess. Friday, day of Venus. and of course Saturday, day of Saturn. They just picked, planets or things into things and named the days after. No real reason there. Okay, can I go on and see? Okay, so next time we will start with a day. Okay, a day in the life. So that will be on page 416, second column, last paragraph. That's where we'll be beginning tomorrow. Next Tuesday. Okay. So sort of an awkward place to do, but let's go on and take a break here. I will go on and pause this for now, and we'll go from current slide, which is basically a blank slide. So where I need it, I'm going to turn on the projector in case I ever do need it. Occasionally we may need to turn the one light off if we need to. All right. Now, first lab, everybody, if you haven't turned it in, at least you've done it. Okay? Okay, so you should be familiar with it. Just a couple things. Exactly what we were talking about at the end of chapter 16, or where we ended in chapter 16, is exactly where we start in the lab for 15 today. It's a little bizarre, but it's okay. Where the sun transits our local meridian, that's our local noon. Okay? The interval from noon on one day to noon on the next day, that's one solar day. When you see S-O-L, sol, solar, sun, that solar panel, solar batteries, that means from the sun, okay? Solar eclipse, the sun's eclipse, okay? So that's one solar day. Noon one day to noon the next day when it crosses the subdivisions of a day, and they talk about all sorts of weird stuff. But here's a couple terms that you should know. All right, remember noon is when the sun crosses our meridian, our local meridian, right? Okay, when it crosses that, it's going up before that, it's coming down after that. That's the peak, as high as it's going to get that day. So before that, we call that before the meridian, which we call ante-meridian. That's the Latin word, and that gives us AM. Not after meridian, ante-meridian, which means before meridian. After that, we don't call it after meridian, we call it post-meridian, PM. So that's why morning hours are AM, ante-meridian, before meridian, and after the noon is post-meridian, PM. Okay? Now, there's some things in here that are just sort of interesting to read. I'll let you read those on your own time. They talk about sundials or gnomons, and we'll talk about a different kind today, not the one that you put in your garden and you follow the shadow. Okay? So, on page 370, that's page 369 and the beginning of 370 is mostly just for you to read on your own at your own leisure. Pretty interesting stuff. Procedure. Part A, we'll talk about the solar day. Solar means based on the sun. Solar, sol, sun. Okay? And then we'll talk about the sidereal day. Sidereal means the stars. I don't know where the connection is there, but that's what it is. So let's start with the solar day. Why does the sun appear to move in our sky at all? Is it really moving? Not anything we can see. It's our spinning of the earth that we're moving. It's not. Okay? It's our rotating on our axis. But that's not all. There's a little bit caused by our moving around the sun that also influences the length of that solar day. We talked about that to great length earlier. Okay? Now, a sidereal day is then one based on the stars. We'll get there a little bit later. Okay, so let's go to question 1 on page 371. The sun moves, and I'm just going to sort of draw I don't know if this will be helpful or not, but I'll draw it. So let's say, okay, that's supposed to be a circle. The sun moves 360 degrees around the ecliptic in a year, in 365 days, right? 360 degrees in 365 days. That's almost 1 degree a day. Not quite, close, but almost 1 degree a day. Okay? So, if it's 1 degree a day, how long do you have to wait between, okay? So 1 degree a day, okay? Every day it's going to move 1 degree further along. So how long is it going to be you have to wait for the sun to cross your meridian one day until the next day? Because we moved 1 more degree past where we were before. 1 degree is, let's see, how many, okay, 1 day is how many minutes? Let's see, let me make sure that's right. Express your answers. Okay. So basically, to give you a visual on this, it's the same thing we had in the book. On the vernal equinox, the sun is on the celestial meridian, right? At noon, that's where it is, right there, okay? 1 day later, the sun has moved up the ecliptic a little bit further. So how long does it take to get from there to your local meridian there? That's what we're asking for. It's moved 1 degree, okay? All right. So, and that was 1 day. Well, 1 day is how many hours? 24 hours, okay? And if you multiply that by 60 minutes per hour, the hours go out, and that gives you 1440 minutes. Okay? 1440 minutes for it to move that 1 degree. Okay? Now.
Excuse me, you said multiply?
Yeah, I multiplied. I'll put the time sign in there. Okay? Oh, you need one? We're on that page right there. Okay. Now, at 3:45, remind me I need to take roll again. Okay? All right. So, okay. Before. Well, what's that? Okay. Okay. I'm going to pull up my calculator for just a moment here. Goodness gracious, I can't get to it from here. I'm going to lose everything. Okay. Okay. So, What's that?
PHS chapter?
Well, just for a minute, I just want to check on something, make sure what I want to say is right. Okay. Yeah. Okay. Thanks. Okay. Now, 24 hours, it moves 1 degree. Okay? Now, that's how many minutes in a day. And if I take that and divide it by 360 degrees, okay, what do you get? Anyone got a calculator?
I got one. Let me put it in. Give me a second.
Okay. 4 minutes. Okay. That's to move 1 degree. It takes 4 minutes. Okay. Okay. And that's what the question is asking. The sun moves 360 degrees around the ecliptic in 365 days. So the sun moves about 1 degree a day along the ecliptic. Okay. Therefore, the sun is about 1 degree east of the vernal equinox. Tell how long you would have to wait until you got back to the situation that's shown in that figure that I pointed you to, figure 48.1b, and it said it expressed it in minutes. So that's why we figured out how many minutes in a day it took that many minutes to go, that's in a day. And you're doing 1/360th of the way around, so that's why you divide it by 360. And you get 4 minutes. It takes 4 minutes for it to move that much further. Okay? Now that's a little bizarre, but it's true. Now, yes?
Yeah, that one behind 2 there, that's a D and A, right?
Say that one more time.
Behind the 1, that's a D and A, right?
This is DA, day, yeah. Okay, abbreviated day, DA. Okay? Now, in figure 48.2, I'm sorry, number 2 on that page, on page 371, figure 48.3, it's a nice figure, okay, you see it? The sun, the earth, and it shows the constellations that pointing toward Leo there. And it describes what's going on there, where the zodiacal constellations are found, heliocentric perspective, as the earth orbits around the sun, and the line of sight of the sun toward the background stars also moves. For example, in the diagram it shows Leo. A month later, it will move so Virgo lies behind the sun. So 1 month later, the earth has moved 1/12 of the way around, and then Virgo lies there. Okay? All that's really true. But they forgot to ask the question. Do you see a question anywhere on page 371 under number 2? No question at all. They left it off, and I haven't got a clue what that was supposed to be. So number 2 is the one white space you don't have to fill anything in because they don't have a question there. Okay. Sorry. So let's move to part A. That was part A, solar and sidereal days. That's all we're going to do on that procedure. Okay? So part A, the analemma. Okay? This is where most of the lab is going to be. The tails of the sun's motion. If you recall, we said that several things come into play with determining a day. You got the Earth speeding up sometimes, slowing down other times in its orbit because it's an elliptical orbit. We have the tilt. That changes things a little bit. lots of things change a little bit. There is another device, and that's going to show up on the next page. It's called an analemma, which also means sundial. But this is a different type of sundial. So if you flip the page over, it's a sort of flat-bottom figure 8. And you see that on page 374. That is your analemma. Now this is a really unique kind of graph, interesting kind of graph, in that it shows so much different information on it. Okay, one thing it shows is the declination of the sun. We dealt with that in the last lab. That's why they said this was a prerequisite. What is the maximum declination of the sun? What's that magic number we use over and over and over? 23.5 degrees north. What day is that on? June 21st, the summer solstice. And see, the top of that figure 8 is right around June 21st. And that is, you read over to the left-hand side, 23.5 degrees, approximately. Okay? You go to the bottom of the figure 8 and get to the bottommost part there. Where are you? Right around December 28th. There's 21st. December 21st, and you're at minus 23.5 degrees. There's your declination of the sun on the left-hand column. The days of the year, every day of the year is listed. They only list them every 5 approximately, but they have light and dark representing every day of the year. Okay? And you see January down here just past December, February, March, April, May, June, July, August, September, October, November, December. You go all the way around the analemma, the figure 8. Okay? Now, the center axis there, it says clock noon. That dark line going north and south there. It doesn't cut the middle of the 8, but close to it. And then you have minutes before clock noon and minutes after clock noon. And you see it goes up to 16, 17, 18 minutes before clock noon, and it goes over to 16 minutes after clock noon. Okay? So you have all sorts of information on this graph. Okay? It's kind of a three-dimensional graph. It's showing days, it's showing declination, it's showing time of day, it's showing lots of information, and we're going to use it all. Okay? Second?
I said I was reading this paper.
Okay. Now, you can read the next page. It has some interesting information. You can follow that. Let's move all the way around to page 376. 376. That's where the next question shows up. Okay? So in summary, right above question 3, it says the analemma graphs the sun's declination. That's the left-hand axis. Daily difference between clock noon and noon of the sun, and that's on the time difference is on the top. The day of the month is on the analemma itself on the figure 8. So let's answer question 3. Go back and look at the analemma here. And it says here, briefly describe the effect of the shape of the analemma if the ecliptic equator angle were actually to increase. It's at 23.5 degrees now, and that's shown here. What would happen if they went to 24 or 25 or 26 degrees? What would happen to your analemma?
On that line, right?
What's that?
Which one you talking about?
The declination of the sun. What's that?
So you talking about that wherever this shape is?
That page right there. And what does it ask? Number 3. Briefly describe the effect of the shape of the analemma. That's the analemma. Okay? If the ecliptic equator angle were to increase. Right now it's at 23.5 degrees. if that were to increase, what would happen to the inner limit?
It will get bigger, wider out there.
Okay, wider or stretched up and down vertically. It would be stretched vertically because now it would go up to say 24 or 20, and down to 24. So it would be stretched vertically. Does everybody see that? If you were to increase that angle, you would stretch it vertically. Right? Everybody see it? Okay. That's a pretty brief description, don't you think? All right. It says, obtain from your instructor the latitude of our location and fill it in below. Remember that from last time? Our latitude here in Bessemer right now is at 33 degrees, 23 minutes, 45 seconds north. That's our latitude right now.
So where's this writing thing?
Number 3, yeah. What would happen to the analemma if the angle were to increase? Stretched vertically. Stretched vertically. Everybody got it?
Yeah.
Okay. And number 4, there's your answer right there. You got it from your instructor. 33 degrees, 23 minutes, 45 seconds north. That's our latitude. Now, underneath that, it says determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. So let's go back. Has everybody got everything off of here you need? Okay. Okay. I'm going to clear this, and we're going to go back to the type of drawings we did before. Okay. Here's the Earth right here. We're standing here in Bessemer, okay, right there. And we are, there's the center of the Earth. Here's this equator. And our latitude is 33 degrees, 23 minutes, 45 seconds. We did this last time. Okay, let's draw our horizon here. Okay, and then we'll draw the celestial sphere, or hemisphere anyway. This is south, this is north. Here's our zenith right overhead. Okay, and we know that the celestial equator is right here. Just the same angle as the equator. Here's the celestial equator, and that is 33 degrees, 23 minutes, 45 seconds. The question is, how determine the altitude over the southern horizon, here's the southern horizon here, the altitude over the southern horizon of the intersection of the celestial equator with our local celestial meridian. This is our local celestial meridian because it goes through the zenith, so what would be this angle right here? We did it last time. Second? You add to be 90 degrees, in other words, subtract from 90 degrees. So rather than 90, I'm going to write that as 89 degrees, 59 minutes, and 60 seconds. Because 60 seconds is 1 minute, that would make it 60 minutes, and 60 minutes is 1 degree, that would make it 90 degrees. This makes the subtraction easier. So subtract from that 33 degrees, 23 minutes, and 45 seconds. And what do you get as a result? Say again? 57 degrees. I think, say again? It's 56 degrees, isn't it?
Yeah.
Yeah, okay. 56 degrees. Y'all trying to lead me astray, okay? 56 degrees, 36 minutes, and 15 seconds. That is the answer to the white space on the underneath number 4. Okay? Why we need that, I'm not sure, but we got it. So, yes?
The diagram, we have to write it down in the test, right? Or
Generally, we're not testing so much on the lab. There are a few things like terms that we use in class and in the lab we'll refer to those on the test too. But most of the time, the lab, like doing these calculations, most of the test questions are multiple choice with a few fill in the blank.
346.
Second.
346.
346. So it's time to call roll again. Let's take a quick break and call roll. Okay, Tiara never made it in today.
My friend not here.
Okay, Matthew is still here. Tacarius Boyd would never have seen. Dante hasn't made it back. I don't know if he's going to. Ty is still here. Justin is still here. Wait, I'm sorry. That's the other Justin. We've never seen Justin Marlin Cosby. Okay. Demetrius is still here. Anstexany is here. I'll probably botch it up again. Okay. Justin Lindley is here. Demetric is here. Ishmael is still here. Darren is still here. Zachary is mostly here. David never made it in today, did he? David Russell. Sarah, I think, is still at the volleyball thing. Max didn't make it in today. DeAndre's still here. And Chris is still here. Okay. So the only one we've lost so far has been Dante. Okay. So we got the roll call. Let's go back to this. So what we're going to do is go back to the analemma, page away, and your answer to step 4, which we just did, to fill in table 48.1. Now, by the way, the latitude of Altegard, Norway is plus 70. We'll come back and get that one in a minute. So, what it asks for here, and by the way, in question 5 it says figure 48.4, but the table was 47.1. And I got the, 48.1, table 48.1, but it said 47.1, so I changed 7 to an 8. So that's why that chicken scratches there. So what we do is go back to February the 15th on the analemma, find February 15th. I'll let you find that. February 15th. Let me know when you found it. And when you do find it, tell me the declination of the sun on that day.
12 to 13 degrees.
13 degrees. Does everybody see that?
Yes, 13 degrees south.
13 degrees south, absolutely. Here is the 15th of February. You see it? February 15th. It's right on that line. Follow that line across. And it's in between 12 and 14, so it's 13 degrees south. So that's what you put in the first blank, declination of the sun. So let's pause for a moment here and do the noon altitude of the sun at our location. So if it's 13 degrees south, here is celestial equator. That's south of what? South of the celestial equator. So if you go 13 degrees south of that, you'll be somewhere about here. Here is the sun on 15 February. Wasn't that 15? Yeah, 15 February. Okay. And you're 13 degrees south of the celestial equator. So what's the altitude of the sun at noon on that day? Subtract the 13 from the 56, exactly. And what would that give you? 43 degrees, 36 minutes, 15 seconds. If you subtract the 13 degrees from that, that would be 43 degrees, 36 minutes, 15 seconds. That would be the altitude of the sun on that day here in Bessemer, Alabama, on the 15th of February. That's the maximum height the sun would get on that day. Make sense? All right. Let's go, and we'll come back and do Altegard, Norway in a bit. Okay? Let's go to June 21st. What's the declination of the sun on June 21st? You should know without looking, but you can look.
Oh, it's 23 degrees.
Positive or north 23.5 degrees. So on June 21st, you're going to be, I probably didn't do that well, this will be 23 degrees 30 minutes. Here will be the sun on June 21st. And if you need the analemma, there it is. There it is. June 21st is right up there. Go across here, and you're halfway between 23 and 24, so that's 23.5 degrees. Okay? So this time we're going to add to 56 degrees, 36 minutes, 15 seconds. Going to add to that 23 degrees, 30 minutes. Okay? 15 to 0 will be 15. When you add 30 to 36, what do you get? 66. But 60 is more than 1 degree, so you have 6 carry 1. Notice that? Okay? Now add the rest of it, and what do you get?
80.
80 on the nose. 80 degrees, 6 minutes, and 15 seconds. So the sun on June 21st, high noon on June 21st, summer solstice, Bessemer, Alabama is going to be just over 80 degrees north. Almost 90, but not quite. Okay. All right.
October
What's that?
15th coming up.
And October, is that what you said, the next one? Okay, he's already jumping ahead to October 15th. What do you have on October 15th?
8 degrees.
8 degrees south of the celestial equator. So you subtract 8 from celestial equator. Celestial equator was at 56, 36, 15. Subtract 8 from that. And what do you have? 48 degrees, 36 minutes, and 15 seconds. So I'm running out of space here. You have the 56 degrees, 36 minutes, 15 seconds, and the declination of the sun. Don't want to get too far ahead. I know we're jumping. But y'all must be anxious to get out of here. Okay, October 15th, the declination of the sun, as you just said, was 8 degrees south of celestial equator. So minus 8 degrees. Okay? So we'll take the 56, 36, 15, that's where the celestial equator is, and subtract 8 degrees from that. So subtract 8 degrees, and that gives you 48 degrees, 36 minutes, 15 seconds. So that's your noon altitude of the sun on October 15th. Then go down to December 22nd. And on December 22nd, what would you say the declination of the sun would be? Right down here.
Think about 23.5 degrees.
That's it. Right at 23.5 degrees. That's below the celestial equator, minus south, or whatever you want to do. So this will be 23, this will be the sun on 22 December. I didn't put them all in here. 23 minus 23 degrees, 30 minutes. I know it's getting crowded here, isn't it? So subtract that from 56:36. So if it's all right with you, I'm going to erase one of these so I can write it in. Is that all right?
Yeah. Whatever.
Okay. I'll subtract 23 degrees. Well, all right. I'm going to subtract 23 degrees, 30 minutes from 56, 36, 15. What does the first give you?
25 degrees.
Isn't it 36?
It's 6.
Huh? From 56.
Oh, 33.
Yeah, okay. 33 degrees, 6 minutes, and 15 seconds. Perfect. So that's your noon altitude of the sun in Bessemer, Alabama on December 22nd. Okay? Now. Okay? Got it?
Which one is it?
What's that? That was December 22nd, noon altitude of the sun at your location. Right there. The declination was minus 23.30, or minus 23.5, however you want to say it, and then you subtract that from your 56, 36, 15. You got that. Now, I got to erase all this stuff and do it for Alsgaard, Norway. You okay? Okay. Where are you lost? On what?
On December 22nd.
22nd. That's what we just said. The declination of the sun was 23.5 degrees, negative 23.30. So the noon altitude of the sun, you subtract that from 56, 36, 15. There it is. 33 degrees, 6 minutes, 15 seconds. Everybody got it?
Sure.
Excuse me. Okay? Excuse me. Okay? Now, are we through with Bessemer?
Yes, sir.
Okay? Want to go to Alsgaard? Put on your jackets, okay? It's going to be cold. Okay? So I'm going to erase a lot of this. I'll try not to erase too much. Okay. This will actually be a bit easier on your subtractions and additions because the latitudes. Okay, one of these years I'll be through. Okay. Almost would have been easier to erase the whole thing and redraw it, wouldn't it? Okay. Let's get us here now. All right, now we're at Altaguard, Norway, and what they tell us about Altaguard, Norway, the latitude of Altaguard, Norway is 70 degrees north of the equator. So here is the equator now, and you're 70 degrees north of the equator, which means the celestial equator is down here. This is 70 degrees north, so this is 70 degrees north. And what we have to do is figure out what this is celestial equator. So what is that above the southern horizon? 20 degrees north. Okay? Not very far up there, is it? Okay? So you already have the declination of the sun on February 21st, February 15th. What was it? South. Okay, so it's 13 degrees south. Is that what you said?
Yes.
Okay, so you subtract 13 from 20, and what is the noon altitude of the sun on February the 15th? 7 degrees. Perfect. See, these are much easier to do. 70 degrees north. Okay, well, it's 70 degrees. Altitude is just measured in degrees. Okay? And what's the declination of the sun on June 21st? 23, and that's a plus on the north side. So you go 23.5 degrees beyond here. So what is the noon altitude of the sun at Altaguard on June 21st?
I think 43.5.
Yes, when you add 20 to 23, 23 degrees, 30 minutes, that adds to 43 degrees, 30 minutes. The one down here, you had 20 degrees and subtracted, what was it? 13. Okay, and that gave you 7?
Yes.
Okay, 7 degrees. So that was the altitude of the sun that day. Okay? How about October 15th? What was the declination of the sun?
8 degrees south.
Minus 8 degrees south. So you take 8 from 20, and what do you get? 12. So 20 degrees minus 8 degrees is 12 degrees. That's as high as the sun gets on that day, October 15th. Well, I mean, altitude is just degrees. Okay. Now, December 22nd, what was the declination of the sun? 23 degrees and 30 minutes. What's the noon altitude of the sun in Altaguard on that day? It never rises. That's below the horizon here. So the sun never rises. Okay? It doesn't rise. It doesn't ever come up. It's inside the Arctic Circle, never comes up on winter solstice. Okay? Doing okay? Everybody up to speed? All right, flip the page. Oh, Rip Van Winkle. We've heard of that dude before. I'm going to erase everything we got here again. Okay, just about there. All right. Okay, let's read about old Rip. Rip Van Winkle awakens from his extended slumber and asks a passerby what year it is so he can determine how long he has slept. I hope y'all know the story of Rip Van Winkle. Never mind. Okay.
Yeah,
You've never heard of it?
I don't even know what
That was early in American history. It was a fable. It wasn't anything that really happened. A guy who supposedly fell asleep and I think slept for 70 years, was it? Or something like that. It's an incredible length, 20 years maybe. I don't know. Some long, long amount of time. And he woke up, and then this is where we catch him here. The passerby quickly responds and then rapidly moves away. I don't know it's how the guy looked or maybe how the guy smelled. 20 years sleeping, I bet you it wasn't too great, okay? Rapidly moves away. Okay, it's a 20-year. Realizing a 20-year snooze might be a world's record, if he's going to contact, what's that place, Ripley, he needs to know more detail. He thinks he should pin down the date as well as the year. So he knows it's about 20 years, so he wants to get the date. He moves out from under the tree where he has slept, winter and summer, that's strange, and measures the altitude of the sun when it crosses his meridian, and he finds it's 44 degrees over the southern horizon. So what he has just done is determine that, I don't know what's happened there. That's not quite right. Okay, there. He sees that the sun on this date is 44 degrees above the southern horizon. That's the sun. He knows that the latitude of his chosen spot on the Hudson River in New York is 42 degrees. So if you know that, this is his latitude, 42 degrees. So therefore the celestial meridian, the celestial equator is going to be 42 degrees. His zenith is going to be 42 degrees above this. So here's the celestial equator. Okay? So the sun is at 44 degrees. The celestial equator is 42 degrees below his zenith. So there we have that fixed. Now, what we need to know is what the declination of the sun is, which is how far it is from the celestial equator. What's the total of these three?
86.
Say again?
86 and 42 and 44 is 86. Okay. But that's 90 degrees.
Right? This is 90 degrees here, and these two added together give you 86. So what's the difference here? 4 degrees. So we know we're 4 degrees. The declination of the sun is 4 degrees south. That's the declination of the sun. Very good. So let's go to our analemma and find when the sun is 4 degrees south. Pick out 2 possible dates that he could have awakened.
October 5th.
October 5th or
March 5th. Right?
March what?
5th.
Is that 5th?
No. 10th.
Okay, around March 10th. October 5th or March 10th. So write those down. Okay?
What date?
The 2 possible dates. On what 2 possible dates could he have awakened? And you said October 5th. You might say 4th or 5th. You choose which one you think it is. Or March the 10th. Possibly 11th, somewhere. You just write down you think the one it is. So write down both of those. Now, he notices that the buds are appearing on the tree he slept under. So what time when buds appear?
March.
That would be the March date. So either circle the March date or write it again or something like that. There's the second part of it. Okay? So there we've dealt with day of the year and declination of the sun. We've done it in several different ways there. So now we move on and we're going to do this. So read that paragraph just about the middle of page 377. Okay? As we saw previously, the analemma gives the daily difference between clock noon and apparent noon when the sun crosses the meridian. As an example, here's the example. Check the analemma in figure, and it's, I think, 48.4. They put 4.3. I mean, they got that really wrong. Okay? To see that on October 15th, you see October 15th? We had it earlier. There it is. If you go up from October 15th, straight up that line, you see you're 14 minutes before clock noon. So anything on this side is before clock noon. Anything on that side, on the right side, is after clock noon. Okay? That's how you do that. Anything to the left of clock noon is before clock noon. Everything to the right of it is after clock noon. Okay? So, now that we've got that down, for the dates given in the table below on page 377, use the analemma in figure 48.3. They got it right this time, except it's a 48.4, I think. 48.4. Close anyway, closer than they were before. Okay. Determine whether the actual sun will cross the meridian before or after clock noon and by how many minutes. Okay? We're on page 377, and I was just reading the directions on number 7. So the first thing we're going to put in that first column is either one of these two words, before or after. We may have one other choice, and that'll be right on the money. Okay? And then the second column will be how many minutes before or after. So the first column is going to be one of 2 or 3 words, before, after, or right on. And the right-hand column is going to be how many minutes. You're going to have to write before or after again. So, yes.
So, we going by the months, right?
What's that?
I'm just trying to read this right because I'm still kind of confused on how to read this time thing. So if January is towards the right side.
Okay, January 10th. We'll start there, okay? All right, on the analemma, find January the 10th. Anyone find January?
Yes.
Way down there, and there's the 10th. So go straight up from January 10th, up that line, and are you before or after? That's the first thing to answer. After. Okay, and then the second column, how many minutes?
8.
8 minutes. Do you see that? Zachary?
Yes, sir.
Okay, you see it?
Short time, but yes, sir.
Okay, you see your after clock noon? You're on the right of clock noon. And then if you go up there, you see you're right at 8 minutes.
Okay, yeah, I see 8 minutes.
Okay, so there was January 10th, before 8 minutes. No, after 8 minutes. After 8 minutes. Okay. February 15th. Anyone find February 15th?
Yes.
Oh, you got it?
Yes.
Are you before or after? After again. Go up that line. Straight up that line. How many minutes after?
12.
15.
What?
Oh, it is.
13 from the looks of it.
How much?
I'd say about 13 minutes.
February 15th.
February 15th is right on that next to the last line, almost, right?
That's 14.
That's 14 minutes, exactly.
The limit is heard.
Okay, after, after, and it's 14 minutes. Everybody got it?
Yes, sir.
Okay. The next date is
April.
April 15th, tax day.
And near my birthday, hashtag Taurus.
Okay. Can you find April
Y'all know
15th?
what Taurus is.
I don't know where it's at.
Yeah, I don't.
Wait, April the 15th?
April
I got it.
I found it.
Okay. Is it before or after clock noon?
Well, it's kind of above it, so I'm going to say
Ah,
before,
yes.
right?
Huh?
I think it's before, right? No.
It's after.
It's after.
But
1 minute.
1 minute.
between
I would say actually less than 1 minute, but you could put down 1 minute, it will be fine. You see that? You're between 0 and that first line, so you're right at 1 minute. After 1 minute, that sounds good. Okay? Let's go to July 30th.
July 30th.
Found July 30th?
3 minutes.
Are you before or after?
After.
After. Okay, July 30th.
I think it's 6.
Yeah, it's 6.
Okay, but July 30th is, okay, I think you were doing June 30th. July 30th is, yeah, about 6 minutes after clock noon. Boy, we're all after, aren't we? How about September 1st?
September 1st, before, from the looks of it. I'd have to say it's gotta be before on it.
September.
So September is, it should be before or whatever, but hey, you know, this week.
Yeah.
I might be wrong.
Would that not be right over?
It sure looks like it's very close to being right on the money. So you can say, if anything, it would be maybe a few seconds after, because it looks like that line maybe just after but it's only a few seconds. It's not even anywhere close to a minute. A few seconds after. So after,
It's September 1st before or after?
I'm sorry?
It said before or after for September 1st.
September 1st. It's so close on it. I would say it's just barely after. And just a few seconds after.
Seconds after?
Yeah, after goes in the first column, and just say a few seconds on the right.
Less than 1 minute.
Okay, less than a minute, exactly. October 30th. Oh, we finally got one before. And how many minutes before?
16.
Oh, trivia.
Uh-oh.
Got it? Everybody see that? Huh?
I think that 30 is for November.
Everybody gets
I think it's over. I think it's right at 15 from the looks of
I
it.
got it.
I would even say 16.
These 30s look.
Kind of movie, yeah.
So this 30's up here. This 30 up here is for September.
Okay, yeah. If you see October there, notice that numbers are increasing as you're going down. 5, 10, 15, 20, 25, 30. So that's the 30 of October.
Okay, so it's
And you go up that line and you're right on
16.
16 minutes before. So it's before 16 minutes. Okay? Everybody got that?
Sir.
Okay? I hope I'm recording. Yes, I am. Good. All right.
Last page.
Last page. Oh, my goodness. How can we be there? All right. Determine the altitude over the southern horizon of the actual sun and the time it crosses your local meridian on the dates in the table indicated. Okay? Dates in the table below. So we're going to have to do altitude of sun. So we go back to our thing, not Rip Van Winkle. So let's delete this again. I wish they'd do all these at the same time. That would be better. Okay. All right. So here we are. Remind me what my latitude is?
The latitude for it is 33 degrees.
33 degrees.
23 minutes.
23 minutes.
45 seconds north.
45 seconds north.
That's our location.
That's our location. That's what it says. When it crosses your local meridian. So,
But that's the Atlantis of the sun?
no, we're just going to calculate it. Okay? So we find our celestial equator by putting it at 33 degrees, 23 minutes, 45 seconds. This is celestial equator because this is actually the equator. So that is this. So we need to also get the altitude of the celestial equator above our southern horizon. And we already did that, so we should have it there somewhere. What is it?
Uh,
56 degrees. Second, 36 minutes and 15 seconds. That's your altitude of the celestial equator. Okay? We need to get the altitude of the sun. So on May 15th, what can you tell me? You can't give me the altitude of the sun, but what you can give me? May 15th. Find May 15th.
15, that's
19 degrees.
Okay, I've got to find it. There's March, April. Oh, there it is, May 15th. Yeah, your declination of the sun is 19 degrees north. So that means the sun is 19 degrees north. I probably didn't go over far enough. Let me get a little, well, we'll just do it. 19 degrees north, or plus 19 degrees. So you add that 19 to your 56, right? 19 degrees, and that would give you what? 75 degrees, 36 minutes, 15 seconds. So that's what you put down as your altitude of the sun on May 15th. Now here we're going to put the time when it crosses that meridian.
Would that be the up here?
Okay? So May 15th, right? You go up and it's 4 minutes what? Before clock noon.
It's three.
It's 3 minutes?
Yeah.
May 15th?
Yes.
Okay. Let me see if I'm reading right. Here's May 15th. Isn't that right on the line below 4?
I thought it was
It's
okay,
on
wait, I
4.
think it is 4. I think it is. Because there's a little.
It said 3.
Right here. It's
I see 3. Because I thought it was the line.
it's 4.
4 minutes before clock noon. So what time would that be? 11:56 a.m. What does a.m. stand for?
After.
Ante-meridian, meaning before the meridian. Okay? All right. What was the next date?
June 15th.
June 15th. Can you find June 15th?
Right on the line.
Oh, my goodness. So what is the... First, we need to know the... What is it? Declination? No, the altitude of the sun.
It's
So we get the declination first. And what's the declination?
23 degrees.
23 degrees.
23 degrees on the nose. Okay?
0 minutes.
So you add the 23 degrees to the 56 degrees. Okay, and that gives you 79 degrees, 36 minutes, 15 seconds. So that's the altitude of the sun on June 15th. If I could find my page.
It's right on the nose. On
Okay,
that
so what time?
12 p.m.
12 noon. That's when it crosses the meridian. 12 noon, right on the nose. You can't tell before or after anything. It's right on it. So let's go to November the 4th. 4 days before my sister's birthday. Okay?
13 degrees.
I can't find, November 4th. I found 5th. The 4th is right the day before that. Okay? And first we'll say what's the declination of the sun.
13 degrees.
I think that's 15, isn't it? Isn't it between 14 and 16?
Yes, 15.
15. So minus 15.
15 degrees south.
So we subtract 15 from 56, and what does that give us? I swear I don't know what I'm doing here.
41.
41. No, 41 degrees. Okay, I have 15. I'm behind. Minus 15. Is that right?
Wait, what?
I've forgotten what I'm. November 4th.
41, yeah.
Yeah, 15. Minus 15. So that would be 41 degrees, 36 minutes, and 15 seconds. Carry those over. So there's the altitude of the sun on November 4th. And what's your...
It's 14 minutes, so I think it's right at 14 minutes.
Really?
Wait, what? Are we
If you
in
go
minutes?
straight up from that November 4th, straight up, isn't that 16 minutes?
Yes.
So 16 minutes before clock noon, what time would that be?
11:44
11:44
a.m.
a.m. standing for
Something meridian.
ante. Ante, which means before. Okay.
Meridian.
Ante-meridian. You know, she's that cute little old ante. All right. Christmas Day.
It is at 20. No, wait, hang on. Uh-oh.
24.
Right on the dot.
Okay. So we know what time. 12 noon. What is our declination of the sun that day?
23 degrees.
It looks like it's 23.5 degrees, awfully close to it anyway. You can say 23 or 23.5, either one. Which you want to use?
23.
Okay, 50, so you want it easy, don't you? 23, subtract 23 degrees from that. That's 33 degrees, 36 minutes, and 15 seconds. That's the altitude of the sun on Christmas Day. And what time?
Noon.
High noon. Guess what, folks?
Lab is finito.
Okay. Well, everybody may not be finished. Let's let everybody finish. And this is a lab. Y'all can work in groups. You can work with each other, ask questions, communicate. Okay, y'all working together? What's that? Okay, that's fine. This is a lab. We work together.
Well, mine's done.
Okay? Okay, folks, anytime you're finished with the lab, you can turn it in, or if you want to take it home and finish reading it or working on it or anything, you can take it home. I don't care. But get it back within a week. Don't lose it. Okay? Thank you.
Going outside.
Okay. All right. Good deal. Thank you. All right. Boy, the grading keeps piling on here. Okay. All right. Now, y'all want another little break? Stretch legs, anything else? Ready for the test? All right, here comes one more lap.
I want to get this test over with.
Okay?
I'm going to turn this building in. Here you go.
All right, good deal.
Yes, sir.
Okay. Now, I know at least one. Okay, at least one person did want to take Chapter 14 test first.
So this is
Research paper in already.
This is okay.
Okay, that's why his name's on it, right?
Yeah,
Okay, good.
I don't know if it
Okay.
is.
And there's his lab. No, there's not. Wait a minute. Dante did his lab, huh? Boy, this sure is lab cooperation time.
Said cooperate.
All right. He wasn't even here and he turned in his lab. Okay. I know at least one person said they wanted to take the Chapter 14 test today. Still do? Okay, you want it? You want it now? Not yet? Okay. Okay. Did anyone else want to take Chapter 14 test today?
This is my man's name.
Okay. Anyone else want to take Chapter 14 test today, or you want to take 15? Huh?
I'm going to take it Tuesday.
I can't.
I'm going to take it Tuesday.
Both of them, or one? Which one? You want to take either today?
I'm taking 15 today.
15 today. Okay. All right. That's what I was asking. Sorry. Okay. So everybody that's here except one is going to take 15 today.
You said we'll be able to post them tonight.
Say that again.
We'll be able to post our tests tonight, right?
You'll be able to.
That's good if you'll be able to post our test tonight.
I can't swear to it. Okay. I'm going to try to be grading while y'all are taking your test, but I've got, if there's many interruptions or other things, and then tonight, we're going somewhere, so I know I'm not going to have any opportunity at home to grade. So I think it's going to be more likely tomorrow. I might be able to get them graded this afternoon while you're taking the test, but I can't swear to it. Hopefully tomorrow. But if when I get over there, the Birmingham West Campus, and they have a pile of stuff that they want done at that time, then I'm going to have to do that and won't be able to get that done then either. So I'm going to try. Sometime over the weekend, I hope to get caught up. But hopefully sooner than that. Okay. Second?
Yeah, like just rate fast. Either redo or
Okay. So, everybody except one is wanting to take the Chapter 15 test now. Is that right?
Yeah.
I
Okay.
want to take it too.
Okay. So let me pass this out. Are y'all ready now? You got your formula and equation sheet, whatever you want to have. Remember, every test you can have those. Okay? Red-eyed? Okay. Okay. Ready yet or not? Not yet. Okay. Ready? Ready? Both ready? And you say you're ready, and then you get your test. All right. And I'm going to shut down Screencast-O-Matic